Alrighty, so welcome back to video 6, Young's double slit experiment 6. Here's our diagram again that we've had on this side of the board for a while, but now we've moved it over here, made it a little bit smaller, because I hope you have some clue now as to what we're looking at and what some of this means. We have our two rays, R1 and R2. Path length difference between them varies as you move around on the screen. A couple of labels here. One is this length L. The other one is our slit separation distance here, D. I want you to remember that D is much, much less than L. Typically, D is a fraction of a millimeter. You know, millimeter, the smallest spacing on the meter stick. It's a fraction of that distance, whereas L is something like a meter or more. Okay, so D is, in fact, much, much less than L. Last lecture, we came up with conditions for constructive and destructive interference. For constructive interference, the condition is that D sine of theta is m lambda, where m is an integer. Okay, 0, positive, negative 1, positive, negative 2. Remember, this is the central maximum is our m equals 0 point, m equals 1, m equals 2, m equals 3, m equals negative 1, m equals negative 2, m equals negative 3, and on down. Okay. Destructive interference, d sine of theta, that is the path length difference. Remember the little triangle path length difference. It's not m theta, m lambda rather, but m plus 1/2 lambda. If that condition is true for any point on the screen, you have destructive interference, and there is darkness at that point. You have a peak and trough meeting up with each other all the time at those points, and so you get no light. Dark. Okay, so these are bright fringes. And these are dark. And remember that m is 0, plus or minus 1, plus or minus 2, yada, yada, yada. How's that show up? Shows up okay. All right, so that was last time. Okay. What I want to do now is just briefly hit on this length here, the distance from the central maximum to the point in question. Okay, that distance is known as y. Okay, here's our point P. And all point P does is indicate which point we're interested in. Okay, point P could be down here, could be the central maximum, could be anywhere. Point P is just the point that we're interested in talking about. Okay, so y tells you the distance between central maximum and the point that we're talking about. All right. And what I want to do is come up with a simple formula for y in terms of the properties on the board. Okay, there's not really a name for y, like horizontal distance or whatever. I wish there were, but there's not one for it, so we're just going to call it y. We're looking for a formula for y. Excuse me. Need to mute my phone. All right. Okay, so here's how it works. What we do to find the value for y is to recognize another triangle. The one that runs here to there to here. How's that for some nice sound effects? Sounds like, well, I better not say. It's kind of ghastly. Let's see. All right, so that triangle right there, that yellow triangle. There's theta. That nice, I'm going to make it a little bit bolder so that everybody can see it, even if you got a small screen. Right there, right there, right there. That yellow triangle. Okay. Notice that triangle right there, that tangent of theta is equal to, right, there's theta, opposite over adjacent. That's y over L, right? Because the length here, the base of the triangle here, has the same length as L. So it's y over L. So a little algebraic hocus pocus here. Y is equal to L tangent theta. Okay. Now, here's a little fact you may not know. Here it is. For small theta, for small values of theta, meaning, 5, 10 degrees or smaller, tangent of theta is approximately equal to sine of theta. Did you know that? You can go to your calculator, put in tangent 5 and tangent and sine 5, and you'll see they come out super close. There's some differences a few decimal places in. If you put in tangent of 1.2, it's going to be equal to the sine of 1.2 for small angles. And theta is a small angle. Okay? It's a small angle. And that's mainly because of the relationship between lambda and d. Lambda is much, much less than d. But theta is small. Okay? I promise you, theta will always be small, so we can make a substitution. Tangent of theta and sine theta are the same. So that means you can take this and say y is L sine of theta. Okay? Because tangent theta and sine theta are the same thing, because theta is a small angle. You can dig into it again. I'm not going to get into it here on the video, but theta is a small angle because the distance d and the wavelength lambda are different by about a factor of 1,000. Wavelengths of visible light are in the nanometers. D is in the order of micrometers, so that's a factor of 1,000. Okay, but if y is equal to L sine theta, then we can make a condition. We can solve this for sine theta. I bring this over. Sine theta is m lambda over d. So we can put these two together. Okay. Sine theta is m lambda over d. We have y equals L sine theta. We can write y equals, let's see, lambda L over d times m. Okay. Y is lambda L divided by d over m. And this is for constructive interference, because we borrowed it from the condition for constructive interference. Okay. So the values of y, okay, for each of the bright points is given by putting that bright point's index here for m. The central maximum has m equals 0. Y is equal to 0 for the central maximum. But as you go out to the m equals 1 bright fringe, you get an m there. And that height, y, is given by lambda L over d times 1. The position of the second bright fringe is twice as much. It's lambda L divided by d times 2. The position of our fringe at point P, y, equals lambda L over d times 3. And all the way up. And all the way down for the negative numbers. Positive y this way, negative y that way. Okay. The condition for destructive interference, y is lambda L over d times m plus 1/2. This is for destructive interference. Okay, so this one here is for constructive interference. That tells you the locations of all the bright fringes relative to the center. Tells you where all the bright fringes are relative to the center. This equation here tells you where all the dark fringes are relative to the center. And in both cases, it's the same old index all the time. M is 0, plus or minus 1, plus or minus 2, yada, yada, yada. Okay. So those are our formulas for y in terms of the variables of the problem. And remember, m is not a variable. Okay. Right now, our point P, right, is m equals 3. But all the other values of m are also taking place. They're all being used at the same time. It's just like the numbers I pass out to y'all. If I pass out a number to each one of you, it'd just be a way of labeling each one of you. The index m simply labels which dark or bright fringe we're talking about. That's it. Okay? Next up, do an example.